Hi there, this is section 2.4, Solutions of Linear Inequalities. Today we're going to discuss vocabulary that we'll see in terms of inequalities. We'll solve and graph linear inequalities, and then we'll also solve and graph compound inequalities. Again, we're going to start out with some definitions today. In an inequality, the solutions are all real numbers that result in a true statement. So that means because we're going to have symbols like greater than or less than, and there could be multiple numbers that make something larger or smaller than something else, we're going to have a range of solutions for answers. If you want to check them, just like any other equation or system, you can substitute that solution back in for the variable and see if you get a true statement. There are some special cases that you may encounter on your homework as far as inequalities go. First of all, a conditional inequality is an inequality that has at least one solution, and most of the problems that you solve will be that. Those are just our regular cases. We have a type of inequality that is called inconsistent, and that is where no real number makes it true. So those are our no solution problems. And then finally, we have a type of inequality called an identity. An identity is where every real number would give us a true statement. So that's our infinitely many case. So just like we had those two special cases with systems, we're going to have the same thing happen with inequalities. You know you have no solution when all of your variables disappear and you're left with a false statement. And you know you're left with an identity or infinitely many solutions when you have a true statement always. So we want to keep those in the back of our mind as we're going through the problems in this lesson. The symbols that you're going to see when we discuss inequalities are greater than, less than, greater than or equal to, and less than or equal to. So if you're not familiar with these, you probably want to write this down. Greater than, less than, greater than, or equal. And this one is less than or equal. One nice way to remember this, it's kind of a silly way that I tell my students, is you can think of an inequality like an alligator mouth. If an alligator has a choice between two things, he's always going to eat the larger thing. So this inequality symbol will always open towards the larger number. All right, so let's start with some basic solving problems. Here we're going to solve and graph, and we're graphing on a number line, you can see with these problems, a linear inequality. The nice thing about these is you can use the same steps as when you're solving an equation with one exception. That exception is when you multiply or divide both sides by a negative number, the sign flips. And when we say flips, we mean it's going to change from a greater than symbol to a less than symbol, or a less than symbol to a greater than symbol. We're going to solve and graph these, and we'll be using interval notation again. Interval notation, remember, is our parentheses and brackets that we used with domain and range. All right, so let's start with the following equation, inequality. 3 minus 3x is greater than or equal to 15. So we're going to treat this just like it was an equal sign in an equation. So nothing to distribute, no fractions to get rid of, no common like terms. So all I can do is get things away from my x here. The first thing I'm going to do is, this is a positive 3, so I'm going to subtract 3 on each side, and I'm trying to get that x alone, remember, is the goal. So I'm going to bring down my negative 3x. 15 minus 3 gives me 12. Then, to get the x alone, I'm going to divide both sides by negative 3. That's the step where we multiply or divide both sides by a negative number. That's the exception in inequality problems. I'm going to have an x on this side. I'm going to have a negative 4 on this side, but because I multiplied or divided both sides by a negative, my sign flips. It's, instead of now a greater than or equal to symbol, it's a less than or equal to symbol. That's our solution if we write it in inequality notation, and you may have some My Math Lab problems that ask you to put your solution in terms of the inequality symbol. If we want to graph that solution on a number line, we would find negative 4. So let's say here's 0, negative 1, negative 2, negative 3, negative 4 is going to be right here. And just like interval notation before, if you have something that's equal, you use a bracket, and if you have something that's not equal to, you use a parentheses. So because we have an equal to symbol, the little line underneath my inequality, I'm going to use a bracket. The solution here, the solution set, is all x values less than or equal to -4. And remember I told you that alligator mouth would help you a little bit. Because the alligator mouth is facing -4, it tells us -4 is greater than all of our solutions that are x. So we want to shade here everything less than -4. So that means if I made a point at -4, everything below that on the number line would be shaded. Where that point is located at, because we decided we were going to use a bracket, we're going to put a bracket facing all the smaller numbers, saying that that's where that stops, and we can include -4 in our solution set. The reason we graph it like this is it's very easy then to put our answer in interval notation. The shaded region represents your solution. So my solution is -infinity, remember we always use parentheses with our infinities, to -4, and -4 has a bracket. So this notation and this notation and this notation, graphing it, all mean the same thing. All the numbers less than or equal to -4. Let's look at another one. I have 3 times the quantity x minus 3 less than 3 minus x. So the first step here is we're going to distribute my 3 through. 3x minus 9 is less than 3 minus x. I don't have any fractions to get rid of. I don't have anything I can clean up on either side, but I do have variables on both sides. So remember, we're going to pick on the little guy. We're going to move the smaller one. I have a 3x and a -x. -x is smaller, so I'm going to add x on both sides. So now I have 4x minus 9 is less than 3. And now I just want to get that x alone. So I'm going to add 9, which gives me 12, and divide by 4, which gives me 3. Nowhere in this solving process did I multiply or divide both sides by a negative, so my inequality sign will stay a less than symbol. To graph that on the number line, I'm going to find 3, 0, 1, 2, 3. And my solutions are all the numbers x that are smaller than 3. So that means everything below 3 will be shaded on our number line. And because it's less than, not less than or equal to, we're going to use this time a parentheses facing that direction instead of a bracket. So my solution in interval notation would be -infinity to 3 with the parentheses. Any number in that range would give me a true statement in this equation. So you could pick a number anywhere in there, maybe 0. 0 should be a solution. And if you plug 0 into the inequality, you should end up with a true statement. So that's a good way to check your answer. Let's try a couple more, some of these fraction ones, just so we can review those steps we used with solving equations. In the first one here, there's nothing to distribute, but I do have denominators that we want to get rid of. One thing that you can do to make this a little bit easier is if you have these fractions that have multiple things in the numerators, you can split them if you remember doing that in a previous lesson. So I can make it x over 3 minus 3 over 3 less than or equal to x over 2 plus 2. Now I want to multiply everything in this problem by the least common denominator, which is the smallest number that both 3 and 2 divide evenly into. So I'm going to multiply everything by a 6. 6 times x over 3 will give me 6x over 3, which gives me 2x. 6 times 3 over 3, and it's negative, will give me an 18 over 3, which just gives me 6, less than or equal to 6 times x over 2 gives me 6x over 2, which is 3x, and 6 times 2, which gives me 12. The next thing I can do is move my variables together. Again, remember, I'm going to pick on the little guy. 2x is smaller than 3x, so I'm going to subtract 2x on both sides. So I have -6 less than or equal to x plus 12. Then to get the x alone, I'm going to subtract 12 on each side. X is greater than or equal to -18. Sometimes people will get a little confused with this notation when the variable's on the right side, so make sure you always think back to that alligator mouth. Whichever way it's opening is larger, so we know that x is larger or greater than negative 18. You can always rewrite this the other way if you like the variable on the left. You can flip the x and the 18, and as long as you flip the sign to make sure it is still opening up towards the x, sometimes it's a little easier for people to see it in that way written. To graph this on the number line, I would find negative 18. So maybe we'll count by threes, negative 3, negative 6, negative 9, negative 12, negative 15, negative 18 we'll put there. And all of my x's, all of my solutions are greater than negative 18, so I shade to the right. It's greater than or equal to, so we use a bracket at negative 18. The solution in interval notation would be negative 18 with a bracket to infinity, meaning any number in that range would give us a true statement if we plug it back into the inequality. All right, let's do one more of these fraction ones. I'm not going to split the fraction here. I'm just going to go ahead and multiply by the least common denominator to show you what it would look like if you want to use this method, but you could always split it if you want. My denominators are 3, 4, and 12. So the least common denominator here is 12. So we're going to multiply 12 times all of my numerators. And really, you can think of it as 12 over 3 times this numerator. So really, it's 4 times 2x minus 1 would be the shortcut here. 12 times x plus 1 over 4. So we can think of that as 12 over 4, which reduces to 3 times that numerator, x plus 1. And finally, 12x over 12 would just simplify to x. The next thing we can do to solve is distribute. 8x minus 4, 3x plus 3 plus x. I can clean up a little bit here. I have a 3x and an x. So that would give me 4x plus 3. Then I'm going to pick on the little guy. I'm going to subtract 4x on each side. So then I have 4x minus 4 greater than 3. Add 4 gives me 7, and divide by 4. Oops, not equal to. Don't do that. I have 7/4 then, which you can always turn that into a decimal. If you just divide those numbers in your calculator, it gives you 1.75. So sometimes that's helpful to graph it on the number line. So 0, 1, and 2, 1.75 is where we want to make our point. Our x values are everything greater than 7/4. So we shade to the right, and it was greater than, not greater than or equal to, so we use a parentheses. The solution in interval notation is 7/4 with a parentheses to infinity. Here are a couple to try on your own. All right, in number 1, we're going to distribute the 4 in. 12x minus 8 less than or equal to 5x minus 9. And the next thing you can do is pick on the little guy. I'm going to subtract 5x on each side. 7x minus 8 less than or equal to negative 9. Then I'm going to add 8 to the other side, which gives me a negative 1. And then divide by 7, which gives you negative 1/7. So 0, negative 1, negative 2. Negative 1/7 would be very close to 0. I would use a bracket because it's equal to, and shade everything below that on the number line. So the solution in interval notation is negative infinity to negative 1/7 with a bracket. For problem number 2, we need to multiply by the least common denominator. And my denominators are 2 and 5, which means the least common denominator is a 10. So I'm going to multiply 10 times the first fraction. Think of it as a 10 over 2, which reduces to 5, and then I still have the 3, and I still have the x minus 6. 10 times 2x over 5, that would be a 20x over 5, which would be 4x. 10 times 12 is negative 120. You can distribute the 3 in. We actually have double things to distribute here. So that would be 3x minus 18. And then distribute the 5 in, which would be 15x minus 90. From there, I'm going to pick on the little guy. So I'm going to move 4x to the other side. 11x minus 90 greater than or equal to negative 120. I'm going to add 90 to the other side. That would give me 11x is greater than or equal to negative 30. And then divide by 11 on both sides. So I'm going to get negative 30 over 11, which is approximately, let's see here, negative 2.8 approximately. So 0, negative 1, negative 2, negative 3. So somewhere between negative 2 and negative 3 is your point. X values are everything greater than negative 2.8 because it's greater than or equal to. We use a bracket also there. In interval notation, your solution would be, make sure you use the exact answer, not the decimal here, negative 30 elevenths with a bracket to infinity. All right, let's start with discussing the intersection method. So we've talked about before how we can type two halves of an equation in our calculator and look for the intersection, and that would be the solution. So this is similar. Let's say f and g are two halves of an equation, and we graph both halves, and you can see we've got g of x and f of x graphed here. The first thing we want to find in this illustration is where g of x is equal to f of x, which is a fancy way of saying when are they the same, which is an intersection point, which is a solution to a system. And that's labeled here for you, negative 1, 3. And if you want the x value where the same, x equals negative 1 is where they're the same. Then in part B, we want to know when is g of x less than f of x. So remember, g of x, if we look at the bottom here, is the red line, and f of x is the blue line. So we want to know for what values of x is the blue line less than, or, oh, excuse me, let me start over. For what values of x is the red line less than or below the blue line? So the part of the red line that's below the blue line is right here. So we want to know where on the graph is that? What x values? Well, it happens right after the graphs intersect at negative 1, 3. And then you can see the x values that are covered because it goes to the right are 0, 1, 2, 3, 4. So every x value greater than negative 1 is where the function g is less than or below the function f. So we can write it like this, or we can write it like the following, negative 1 with a parentheses to infinity. Either of those would be correct. The second one is the one that, of course, is in interval notation. The other question we want to know is where is g of x greater than f of x, greater than or equal to? So this is the opposite now. I want to know when is the red line above or equal to the blue line, and that occurs on this portion of the graph. So my solution is all the x values that are less than or equal to, because we're allowed to be equal to, negative 1 is where, again, function g is greater than or function g is above function f. To put that in interval notation, that would be all the numbers negative infinity to negative 1. And again, because we're allowed to be equal to here, we use a bracket. So you'll notice in all three of these, it's all just a key point that we're using to jump off of. That intersection point we find first, negative 1, and then on one half of the graph, one function is below the other, and then on the other half of the graph, that function is above the other. So now we're going to try to do this with our calculator. When you're doing this in MyMathLab, it will either say intersection method or x-intercept method. I will show you both, but nobody's going to be checking what you're putting in the calculator. So if one of these methods you prefer to the other, go for it. All right, so in the calculator, remember either of these methods can be used. Let's start with, oop, where'd that go? There's a picture of my kids. Well, you might as well see it. There they are. Aren't they adorable? Okay, so let's start with the intersection method because we've been talking a lot about intersections lately. So we're going to go to y equals, and we're going to type 1/2 of the equation or the inequality in y1 and the other half in y2. Remember alpha y equals, we'll bring that fraction up for you, 2 parentheses x minus 4 over 3. And then in my second equation, alpha y equals, enter, 3x over 5 minus 8. And I'm not sure if we had anything else over there. I think that was it. Yep, that's all we had. Okay, and I'm also going to make a note in my calculator, the left side is going to show up in blue and the right side is going to show up in red. So actually, I think I can just drag this over maybe. There we go. To remember what's going to look like what. All right, so we're going to hit graph, maybe even zoom 6 to make sure we're in the default window. And there's our picture. Unfortunately, I can't see an intersection. It looks like they're getting closer together on the negatives here. So maybe let's change our window. We can even zoom out. Let's do that. We haven't played with that very much. So you can zoom in or zoom out anywhere you want. If I choose zoom out, number 3, it'll zoom out around my origin, which is a good place to start. If you had a specific place you wanted to zoom out on, actually maybe let's go down a little bit because I think the intersection's down there somewhere. There we go. Hit enter. It'll zoom out there. Oh, I'm close, but not quite there. So I'm going to zoom out one more time. Zoom out, enter. And there's one, and there's the other. Okay, so let's find that intersection point first. Second, calculate, intersect number 5, and we're just going to hit enter 3 times. Enter, enter, enter. And the intersection point, most importantly from that, is the x value. The x value of -80 is where they're intersecting. So the point is -80, -56. We want to know when the first piece, or the blue, is greater than or equal to the second piece, or the red. So you can see on the left side of this graph, the red is above the blue, and on the right side of this graph, the blue is above the red. That's what we want. We want to know where the blue is above the red. So all of these x values to the right of that intersection point are our solution. So we say all the x values greater than or equal to, because again, we're allowed to be equal to in this problem, -80. And that's our solution. If we wanted to write in an interval notation, it would be -80 with a bracket to infinity. Now let's go back to the calculator. I'll tell you that this is the method that I prefer, but I can also show you the x-intercept method if you prefer that. If you go back to y equals, I'm going to clear out what I have in y2, and I'm going to type the whole equation in y1. Now remember, when we did this before, everything has to be on one side of the equation. So let's actually edit that a little bit. If I want to use the x-intercept method, I have to play with the equation. I'm going to keep that 2x minus 4 over 3 on the left side. I'm going to subtract 3x minus 5 to move it to the left. I'm going to add 8 to move to the left. It'll still be greater than or equal to. I won't have anything on the right, so 0. So that's what I'm going to type in my equation. So I can keep what I have there, minus alpha y equals, enter, 3x over 5 plus 8. And then hit graph. And I should be able to see it still perfect. I'm looking for where it's crossing the x-axis. And I can see where it's crossing the x-axis is on the left side of the axis here. Okay. So let me drag that down a little bit. In your calculator, you can calculate the x-intercept by hitting second, calculate. Another word for x-intercept is a 0, number 2. And this is where you have to tell your calculator what you think. So I'm going to say on the left side, I think is negative 100 approximately. And you can see I've got an arrow that shows up there pointing towards the intersection. Right side, 0, I'm pretty confident is on the right side. And then I hit enter. And again, you can see we get that same thing, that negative 80 that we got on the last example. Now we want to know in this problem, when is the function greater than or equal to 0, which pretty much means when is it positive or when is it above the x-axis. And again, you can see everything to the right here is positive or greater than 0 above the x-axis. So again, I end up with that same solution, x greater than or equal to negative 80, or again, negative 80 to infinity. So two different methods to get the same answer, all using your calculator, which is nice if you get stuck on some of these algebra methods. Okay, try this one on your own. Solve using your calculator using either method. All right, I'm going to use the intersection method, y equals. I'm going to clear out what I had in there. My first piece is 5x plus 2, and my second piece is 2x plus 6. I'm going to just hit zoom 6 to go back to my standard window, and I'll zoom out if I need to. Actually, I can see the intersection here already, so we're good. Just to review here, I'm going to put this over here so I remember what's what color. Okay, so the left side of my equation is blue on the graph, and the right side of my equation is red on the graph. We want to know when is blue less than red. If you don't have a color calculator, it's a little more difficult because you have to just pay really close attention to what shows up first and what shows up second. So to do this doing the intersection method, we're going to hit second, trace, find the intersection, number 5, by hitting enter, enter, enter. And it tells me my intersection is 1.3 repeating for the x value and then 8.6 repeating. Again, the x value is what's important here. And you can either say 1.3 repeating, or that's a common fraction, 4/3 is what I'm going to use here. So now, again, we want to know when is the blue less than the red, or when is the blue below the red. It's all the numbers on the left side of the intersection. So that means all of my x values that are less than my intersection value, 4/3. Or I could say negative infinity to 4/3 with a parentheses is my solution. Okay, next we're going to talk about compound inequalities. Compound inequalities are when you have an or an and statement combining the two parts of your inequality together. We say or means union, which means anything that's a solution to one piece is a solution to the whole. So your solution will be both statements put together on the same number line, and anywhere that's graphed is a part of your solution. And statements represent intersections. So your solution will only be what the two inequalities have in common, or the overlap when they're graphed. So let's look at a few examples. This first one is an or statement. We're going to worry about that at the end. Right now we're just going to solve these two pieces individually as we have been doing. So on the left, I'm going to add 5, which gives me 12. And then I'm going to divide both sides by 3, which gives me x greater than or equal to 4. I'll just bring down my or statement and solve the other one. To solve for x on the right, my 5 is positive, so I'm going to subtract 5 on both sides. 1 minus 5 gives me negative 4. And then I'm going to divide both sides by negative 2. Now remember, that was one of our special cases. If we divide both sides by negative 2, it flips my inequality sign. Negative 4 divided by negative 2 gives me 2. So now, to graph an OR statement, you graph both of them on the same number line. If they overlap, they overlap. If they don't, they don't. It doesn't matter. So I want to graph x greater than or equal to 4. So 1, 2, 3, 4, which means 4 with a bracket and shade to the right. I want to graph x values less than or equal to 2, which means 2 with a bracket and shade to the left. If it's an OR statement, anything that's graphed is your solution. So we have two different solutions, or parts of my solution set, I should say. The first solution set is negative infinity to 2. The second solution set is 4 to infinity, both have brackets. And then just like domain and range, we use a union symbol to combine the two together. And that's your answer in interval notation. Let's look at another one. Now we have an AND statement. Again, we're going to start by solving both individually. For the inequality on the left, I'm going to distribute 2 in. That gives me 6 minus 2x minus 3. Then 6 and negative 3 I can combine together, so negative 2x plus 3. Then I can subtract 3, which gives me 2. And then I can divide both sides by negative 2. Remember, if we divide by a negative, we flip that inequality sign. So I get x greater than negative 1. Bring down my AND statement. To solve on the right, I'm going to distribute my 2 in. 2x minus 10 plus 7 less than or equal to 3. Negative 10 and 7 are like terms, so I can say 2x minus 3 less than or equal to 3. Add 3, I get 6, and divide both sides by 2, I get x less than or equal to 3. To solve this now, we need to look for where these two intersect or overlap. So it's helpful to graph them both on the same number line. First, I have x greater than negative 1, so if I find negative 1, I'm going to put a parenthesis there and shade to the right. Then I have x less than or equal to 3, which means I need to find 3 on my number line, put a bracket, and shade to the left. Your solution is anywhere where the shading overlaps. So you can see here what's both red and green is between negative 1 and 3. And we use the symbols that are on the ends. Negative 1 to 3. Negative 1 with a parenthesis, 3 with a bracket. That means any number between negative 1 and 3 would make both of these equations true. So you could pick something like 0, plug 0 into both equations and make sure it works. Now, what's interesting about this is if I made this an OR statement, my answer would actually be all real numbers because I would have the entire number line shaded. So that would be our special case here. If I had an OR statement, again, the whole number line shaded, my answer would be infinitely many or all real number solutions. Okay, let's try one more. This last one is an OR statement. I'm going to start by multiplying everything on the left by 2 to get rid of that fraction. 2 times a half gives me 1x, minus 2 times 3 gives me 6, 2 times 5x gives me 10x. Then I want to pick on the little guy, move the smaller one, so I'm going to subtract x on each side. I have negative 6 less than 9x. And then I'm going to divide both sides by 9. So that gives me x is greater than negative 2/3. Bring down my OR statement. Then I'm going to multiply everything by 5. 5 times 2/5 gives me 2x. 5 times negative 5 gives me negative 25. And 5 times 6x gives me 30x. Then I'm going to subtract 2x on each side. Negative 25 is greater than 28x. And then divide both sides by 28. So I have x less than negative 25/28. 28ths, which is very close to -1. If you type that in your calculator, it's closer to -1 than -2/3 is. So now let's graph these. If I graph the first one, I want all the x values greater than -2/3. So let's say, oh, these are close together. Let's do -0.25, -0.5. I'll count by quarters here, -0.75, and there's -1. Okay, so -2/3 is a little between -0.5 and -0.75. I want all the x values greater than it. Think about the alligator mouth. X is bigger than -2/3. So it's going to look something like that. Okay, then I want to do all the x values that are less than -25/28, which again is very close to -1. Again, it's just strictly less than. So I'm going to shade below. And again, if we have an or statement here, anything on the number line that's shaded is a solution. So my solution here is -infinity to -25/28 was that number that was graphed. Then a union symbol, -2/3 to infinity. Now what's interesting about this problem is if I changed it to an and statement, there would be no overlap at all. So your answer would be no solution. So that would be what another special case would look like. Okay, the next problems that we're going to talk about are called double inequalities, which are actually compound inequalities. They're an and statement in disguise, and there's two different ways you can solve them. If you just have a single variable, like in the problem on the left, you can isolate that variable. The only difference here is we don't have two parts to an inequality, we have three. So whatever you do to one part, you have to do to all three parts. So let's talk about getting that x alone in the middle. The first thing I'm going to have to do is multiply everything by 5 to get that 5 out of the denominator. So that would mean I have -5 less than. In the middle, the 5's would cancel and give me 2x minus 3 less than or equal to 5 times 0, which is just 0. Next, to get the x alone, I'd have to add 3, but we're going to add 3 to all three pieces. So I have -2 less than. In the middle, my 3's cancel. And on the right, 0 plus 3 gives me 3. And then I'm going to divide everything by 2, which gives me -1 x and 3/2. What's nice about these is you can see that x is between -1 and 3/2. That's your solution. -1 with a parentheses because it's not equal to, and 3/2 with a bracket because it's equal to. And if you graph that on a number line, here's 0, here's -1, here's 1, here's 2, here's 3. -1 would have a parentheses. 3/2, which is 1.5, would have a bracket. And it would be everything between them. The only thing you have to be careful about in these problems is if you see an inequality like this, the inequality symbols should always point in the same direction at the smaller number. If they don't point in the same direction, or they're not pointing at the smaller number, it's automatically a no solution. It's an impossible case. So again, they should point in the same direction at the smaller number. Now let's say you have a compound inequality like the one on the right here where there's multiple x values. It's very, very difficult to isolate an x when there are three parts to an inequality. We can do it when there's two parts, but not three. So instead, we're going to split this and break it apart into the and statement that it represents. You're going to use the middle part twice. The first part tells me that 5x needs to be less than 3x plus 1. The second part tells me that 3x plus 1 is also restricted because it must be less than 4x minus 2. And again, these will always, always, always be an and statement if you split them up like this. So now let's solve each piece individually. I'm going to subtract 3x. That would give me a 2x less than 1. And divide by 2, I get x less than a half. On the right, I'm going to subtract 3x on both sides. 4x minus 3x gives me 1x. And then add 2. I'm going to get x is greater than 3. Bring down my and statement. Now remember, with an and statement, we're looking for where they intersect. So we want to graph both of these. On the number line, I'm going to graph them in two different colors. First, I have x less than a half. So I know I'm going to have to get up to 3. Let's do that. X less than a half would be a parentheses at a half. Shade to the left. Then I have x greater than 3, which means I'm going to have a parentheses at 3 and shade to the right. It's an and statement, which means we're looking for an intersection or what they have in common. There is nothing that these have in common, so your answer is no solution. Okay, try these two on your own. For the first one, you should have subtracted 1 and then divided by 3. Bring down the and. For the second one, you should have added 5 and divided by 2. If you want decimals for these to help you graph it, it's about negative 2.6 and 5.5. X less than negative 8/3. So let's see here, negative 1, negative 2, negative 3. Somewhere between negative 2 and 3, you should have a parentheses, and it's all the x values less than that, so shade to the left. And then 5.5, 1, 2, 3, 4, 5, let's say 6 is there. Between 5 and 6, you should have a parentheses and shade to the right. Nowhere here do we have anything in common, so your final answer is no solution. Again, if this was an or statement, we would list both groups, but because we're looking for an intersection, no solution. For the second one, you can isolate the x in the middle. So you should have added 5 on each piece. That gives me 22 less than or equal to 3x less than 36, and then divide all 3 pieces by 3. So I have 22/3, which by the way is 7 1/3, if that helps, less than or equal to x less than 12. My inequality symbols are pointing in the same direction at the smaller number, so this is our solution. Our solution is going to be 7 1/3 or 22/3 with a bracket because it's equal to, all the way to 12 with a parentheses. To represent that on the number line, let's see, I'll maybe count by 2's here. 2, 4, 6, 8, 10, 12. It would be 7 1/3, so maybe here with a bracket, all the way to 12 with the parentheses, and everything in between them would be shaded. The last few problems that we're going to go through are applications of our inequalities. Let's start with this example. The equation F equals 9/5 C plus 32 gives the relationships between temperatures measured in degrees Celsius and degrees Fahrenheit. We know that a temperature at 32 degrees Fahrenheit is freezing. We want to use an inequality to represent the corresponding freezing temperature. So at or below 32 means my temperatures in Celsius need to be, or in Fahrenheit, excuse me, at or below 32. My Fahrenheit temperature needs to be less than or equal to 32. So what we're going to do is make our Fahrenheit temperature, again, at or below, less than or equal to its equivalent Celsius temperature. We're going to put our 32 in for F. And now when we solve this inequality, this will tell us what Celsius temperatures will give us a freezing temperature. To solve, we're going to subtract 32 on each side, and those 32's cancel. So you're going to have 0 less than or equal to 9/5 C. To solve for C, you can divide by 9/5, or often when we have a fraction multiplied by our variable, we multiply by the reciprocal, flip it on both sides. Either way here, you would get C greater than or equal to 0, which means a Celsius temperature greater than or equal to 0 would be what we're looking for in this problem. Okay, let's look at an application for inequalities. Here we have F equals 9/5 C plus 32, and it gives the relationship between the temperature is measured in Celsius and degrees Fahrenheit. We want to know what temperature at or below 32 degrees Fahrenheit is freezing, and we want to find the freezing Okay, let's do an application problem. The equation F equals 9/5 C plus 32 gives the relationship between temperatures measured in degrees Celsius and degrees Fahrenheit. We know that a temperature at or below 32 degrees Fahrenheit is freezing. Use an inequality to represent the corresponding freezing Celsius temperature. So we're first here going to solve for what temperature in Celsius is equivalent to the freezing temperature in Fahrenheit, which is 32. So we're going to set up 32 equals 9/5 C plus 32. To solve for C, we're going to subtract 32 on each side, which will actually get them to cancel. So you'll have 0 equals 9/5 C. And then from there, we're going to multiply by 5/9 on both sides. Multiply by that reciprocal. The other option here is you could divide by 9/5 on each side, but sometimes dividing by a fraction gets messy. 5/9 times 0 gives me 0. So that means 0 degrees Celsius is equivalent to the freezing temperature in Fahrenheit. We want to use an inequality to represent all freezing temperatures. So if the Celsius temperature is less than or equal to 0 degrees, we know that it is freezing. And we know that if it's greater than, it's not freezing. Let's look at another one. If John Deal has a course average between 70 and 79, he will earn a grade of C in his algebra course. Suppose that he has 3 exam scores of 78, 62, and 82, and that his teacher said the final exam has twice the weight of the other exams. What range of scores on the final exam will he need to earn a grade of C? In this setup, when we write our inequality, and we can start by writing the inequality, we're going to have a range that he's allowed to earn, and it's anything between a 70 and a 79, and we assume that a 70 and a 79 will also give him a C, so we're going to say equal to. Remember, when you set up these compound inequalities, the inequality symbols always point in the same direction at the smaller number. So that'll give us a range of C's. To calculate his grade, it is an average of all of the courses and all of his, not the courses, the exams, excuse me. So it sounds like he has scores of 78, 62, 82 so far, plus the exam will be twice the weight of the others, which means whatever the exam is, and let's use an E, will count twice. To find the average, we're going to divide by how many scores there are, and you can see there are 5 scores total. Let's solve the problem. First, we're going to multiply everything by 5 to get rid of that denominator. 5 times 70 is going to give me 350. 5 times everything in the middle is just going to cancel that denominator, so I have 78, 62, 82, and we can actually add E and E together. Let's make that a 2E. And then 79 times 5 gives me 395. The next thing I'm going to do are add my like terms together. If I add all of his scores that he has so far, 78, 62, and 82, I'm going to have 350 less than or equal to 222 plus 2E. From there, I'm going to subtract 222 from everything. So 350 minus 222 is going to give me 128. I still have a 2E in the middle. 395 minus 222 gives me 173. And then finally, divide everything by 2. 128 divided by 2 is a 64. And 173 divided by 2 is an 86.5. So the range of scores that he needs on the exam to earn a grade of C overall for the course are between a 64 and an 86.5. You could also use this to say then if he gets below a 64, he'll earn a D, and if he gets above an 86.5, he'll earn a B. So it's a good way to figure out what you need in a class at the end of the course for the exam to get the grade you're shooting for. Let's look at another one. Deb Cook is given the choice of two positions, one paying $3,100 per month and another paying $2,000 per month, plus a 5% commission on all sales. What amount must she sell in a month for the second position to be more profitable? Again, we see a word like more in this problem. Less than, greater than, more than, less than. So we want to use an inequality to represent that. The two positions. That's going to be the two sides of our equation. The first position, she earns $3,100 per month. So we'll say M. In the second position, she earns $2,000 per month plus a 5% commission on all sales. On all sales made during the month. Actually, I think I'm going to take out those M's because I think we're just calculating it for 1 month. So we don't have to worry about the per part there. So the first month she just makes 3,100, or this first position she makes 3,100, period. The second position she makes 2,000 as a base salary plus 5% on her sales. So we're going to use sales as a variable. And let's call that X. And again, you can see I used that 5% as a decimal 0.05. We want the second position to be more profitable. So we want the second position to be greater than the first, and that creates our equation. From here to solve, I'm going to subtract 2,000. That gives me 1,100 less than 0.05x, and then I'll divide both sides by 0.05. So 1,100 divided by 0.05 gives me 22,000 is less than X. So that tells me that she needs to sell more than $22,000 to make the second position more profitable from the first. So this is a good example of if you had two job offers and one salary was compared to another salary. You could use this to figure out how much maybe you would need to sell in commissions or sales in general to make one more than the other. And if you know, well, it's probably more likely that I'm only going to sell $10,000, then you would take the first position because that would be the better deal. Or if you know that you're going to make $30,000 or $40,000 worth of sales, it's probably better to take the second position. Let's look at another problem. A home purchased in 1996 for $190,000 was appraised at $270,000 in 2000. Assuming the rate of increase in the value is constant, which that tells us it's linear, we've talked about that a lot, we want to do the following. First, we want to write an equation for the value of the home as a function of the number of years X after 1996. So we need to write an equation, and this is going to go back to a few sections ago. We're given two pieces of information that go together, which means we're given 2 points here. 1996, or year 0, because it's 0 years after 1996, the value of the home was $190,000. In 2000, which is 4 years after, the value of the home is $270,000. To write an equation for this, the first thing that we're going to have to do is find the slope. y2 minus y1 over x2 minus x1. 270 minus 190,000 divided by 4 on the bottom is going to give us 20,000. We also know the y-intercept in this problem because remember a y-intercept is when an x equals 0. So that's 190,000. So our equation is y equals 20,000 x plus 190,000. Part B says, assume the equation in Part A remained accurate. Write an inequality that gives the range of years until the end of 2010 when the value of the home was greater than 40,000. Remember, y here is the value of the home. So we're going to take our equation and we want to know when that is, again, greater than 400,000. So to solve, we want to subtract 19,000, on both sides, or 190,000. Ooh, so many zeros in this problem. So 400,000 minus 190,000 is 210,000. And then from there, I'm going to divide both sides by 20,000. And that is going to give me x is greater than 10.5. So that means 10.5 years after 1996, which will round that to approximately 11. 11 years after 1996, the home will be worth more than 400,000. So 11 years after 1996 would be 2007. And again, we wanted to make a range until the year 2010. So x values between 2007 all the way up to exactly 2010 would be when the home was greater than 400,000. Does it seem reasonable that this model remained accurate until the end of 2010? That's a yes or a no, depending on what you feel is appropriate. I would say yes, because it grew at a linear rate, and 2007 to 2010, the values were around 400,000, give or take a few $1,000s. So I would say yes for this problem. Now, if you found that the home was only greater than 400,000 after 2015, then it wouldn't be reasonable for 2010. Let's do one more together. And this one, we're just going to set up the problem, we won't solve. A large hardware store's monthly profit from the sale of a PVC pipe can be described by the equation P of x, remember we use that for profit a lot, equals 6.45x minus $9,675, where x is the number of feet of PVC pipe sold, and of course P again is the profit. What level of monthly sales is necessary to avoid a loss? So if you want to avoid a loss, your profit needs to be either equal to 0 or greater than or equal to 0. So we're going to take our profit function and make sure whatever our profit is greater than or equal to 0. Now, if this problem said what level of monthly sales would result in a loss, instead of greater than or equal to, we would use less than 0, because we would want to know when would our profits be in the negatives instead of the positives or 0. And again, you can solve this on your own if you'd like to for extra practice, but